everyone, welcome back. And today we're going to look at our physical world. And your notes are split between the Earth itself, which is what we'll look at in this first video, and then looking at climate and also soil and vegetation. So let's get started with the Earth. And the first thing we need to understand about the Earth is where is it in our solar system? And y'all have had this before, and you know we're the third planet from the sun. But we are one of the inner planets, and these are the terrestrial planets, and this is Mercury, Venus, Earth, and Mars. I missed a comma. The outer planets are our gas giants, and those are Jupiter, Saturn, Uranus, and Neptune. Now, a great way to remember the planet is Mom visits every Monday, just stays until noon. So that's one way that we can learn that, and an easy way to help us remember it, kind of like the way we remembered the 5 themes of geography. The only one missing that used to be there is Pluto, and they have decided that it is no longer a planet. Poor Pluto. The Earth has a structure, and I have included some diagrams here for you to look at, but the crust is that top layer, and it is made up of the dirt. It is 19 to 37 miles thick, so comparatively speaking, it is just that. It is a crust, and it's not very thick at all, even though 37 miles down is pretty big to me. But it also has the lithosphere as part of it, and this is 30 to 90 miles thick. And it's solid, but it is the crust and the upper mantle. So it's kind of that in-between area between crust and mantle. The mantle is a lot thicker. It's about 1,800 miles thick, and it is made up of solid rock, and it is hot, super hot. It is making part of this up is the asthenosphere, and it's about 400 miles thick. And here you have some partially molten upper mantle material, and really it says here that it behaves plastically and can flow, or it adds some elasticity, lubricant, I guess you could say, that this is what allows the plates to move. Okay, and that's getting into our continental drift, because we do know that our continents move. We've talked about that, and we have mentioned Pangaea, but there's also, between Pangaea and us today, you have Laurasia and Gondwana, and of course our modern world today. So that's the drift. This is a theory. There is no actual proof that it happened, but it is theory. So when it talks about that continental drift theory, this is what I'm talking about. And you have this diagram in your notes, on your notes guide. That outer core is also 1,800 miles thick, like the mantle, but it is liquid. And you have your inner core, which is comparatively small, 760 miles thick, and it's solid. Okay, I'm not going into a lot of this. I'm just kind of giving the notes to you, just so you can have some kind of basis. But again, you can look at these diagrams and get an idea. Our water, our land, and our air is, and again, you have this also on your notes guide, this diagram over here. You've got your lithosphere. This is the Earth, and this is the land. This is 30% of the Earth, okay? You have your hydrosphere, which is bodies of water, and this is 70% of the Earth. And then above all of that, you have the atmosphere, which is the gas or the air that surrounds the Earth. Anywhere that life exists is called the biosphere. So you do have life that lives on the Earth, in the Earth too, in the water, but also in the air. So all of this together is our biosphere. I mentioned it a second ago with the continental drift theory, but our Earth is not static. It doesn't stay still. It's very dynamic. And a lot of internal forces are at work with the earth, and one of those is the idea of plate tectonics, and that's the movement of our crust. And these happen 4 ways. You've got subduction. Right here you can see one. You've got collision as the last one, and that's exactly what it sounds like, but here one is actually going under another. You have spreading. Okay, they're just moving apart. Then you have lateral sliding. Okay, so you've got these 3, and then collision. Oops, let me go back. Sorry about that. Collision, what I just mentioned a second ago, which is just kind of colliding. When cracking occurs is called faulting, and we have faults. We talk about the San Andreas Fault out in California, but this is all a part of the plate tectonics. And above, at the top part of this, you see your different plates. Okay, your Eurasian plate, African plate, Indo-Australian, and again, some of this kind of gets into why there may be different continents. We talk about the different continents. Different countries use different names. Maybe not names, but they put Europe and Asia together. So anyway, but as those plates kind of grind together or slip past each other or collide and hit each other at those faults, the earth shakes or trembles, and that is an earthquake. And we can tell how big one is based on a seismograph. And you can tell also where the epicenter is. Where did it originate? And I don't have epicenter here, but that's a term that you typically hear when we talk about earthquakes. A lot of times, depending on where the earthquake is, it can cause a tsunami. Now, it could be that there's an earthquake in the ocean that causes it, or it could be one that's right here on a shoreline that causes it. But this is a giant wave in the ocean. It is not a tidal wave. It is just a giant wave caused by the displacement of water. And it travels from that epicenter of an earthquake of speeds of up to 450 miles an hour. And the waves it produces could be 50 to 100 feet or higher. And a lot of times, if you look at pictures of an area, you can tell beforehand because the water on the shore will disappear because all of that water is being sucked out and into that wave, and then it just kind of seems like it just kind of washes ashore, and it doesn't come like we think of waves coming. It just kind of all rushes in there. If you ever have a chance, and I'll try to show one in class, but see if you can look up a video of a tsunami. It's a scary thing. Other internal forces, one is a volcano, and y'all know what volcanoes are. Now they look different. They're not all the cone shape, but here you have magma, gases, and water from the lower part of the crust or the mantle collecting in underground chambers, and they eventually are going to pour out of a crack in the Earth's surface. Now, magma could flow out onto the land slowly and cool, and that's lava. Lava is magma that reaches the surface, but you can also have violently erupting volcanoes, and that spews hot lava, gas, ash, dust, and rock out of the Earth's crust. Mount St. Helens that erupted in 1980-81, it was a typical cone-shaped, and it just blows, and it just spews all of that lava and gas and ash, and it just kind of whoosh, it does lead to some utter destruction. Whereas if you can look in Hawaii, a volcano out there recently, it just kind of is gently, I say gently, but I mean, it's still destructive because it's so hot, but it's just kind of slowly, you've got lava slowly kind of moving across the land, and that's kind of interesting to see too. You do have the Ring of Fire, if you look up here on this map. And you'll notice that the United States is a part of that. Our west coast is within that ring of fire. But this is a zone around the Pacific Ocean. And this is where most of the world's active volcanoes are. Now, this is not all of the world's active volcanoes, by no means. We do have volcanoes over in Europe. And again, I don't mean to make it sound like these are the only ones. They're not. But these are the most active. This is where most of our active volcanoes in the world are. And it's interesting because 8 of the major tectonic plates meet in this zone. And you have a lot of volcano and earthquake activity here. Okay, this is an interesting thing. Now, again, it's not the only place because we have, you know, here you would have a lot of geysers and stuff, but we have geysers on the interior at Yellowstone, and we have volcano in Yellowstone. So, I mean, again, it's not to say that this is the only place you have volcanoes, but these are just the most active. External forces. Understand a few things. One, and I'm going to say this over and over again, climate is long-term and weather is short-term. And we talked about that briefly. But just keep that in mind. Climate, when we're talking about climate, is something that takes place over a long period of time. Weather is short. Weather is short-term. We're looking at what's happening now. So some external forces that change the Earth. One is weathering. And this is physical and chemical processes that change the characteristics of rocks on or near the Earth's surface. And this can occur very, very, very slowly over a lot of years. The first one that we think about, I think the most, is mechanical weathering. This is the process that breaks rock into smaller pieces. It doesn't change the composition of rock, it just breaks it into smaller pieces. And you see this a lot of times with erosion. You've got water, wind, glacial erosion. All of these things will just break rock down into something smaller. Chemical weathering, though, you change the actual substance. And carbonation can do this. Oxidation, adding oxygen can do this. Acid rain, having rain that has a high acidic value in it can actually change the composition of rocks. Okay? And again, like I said over here with erosion, it's another form of changing externally. But this is when weathered material is moved by the action of wind, water, ice, or gravity. Okay, but this is all a part of forming soil, and we'll look at soil a little while later in the next video. We also have a water cycle, and again, you have this picture over here, and I'm not making this into this big story or anything. This is just information that you need to know about how different systems work on the Earth. So in the water cycle, you have evaporation from oceans and lakes and streams. The sun heats the Earth, causing that evaporation, and it goes up. Okay, and then it's going to cool and condense into water vapor in the clouds. Okay, and then it is going to fall to the earth in some form of precipitation, whether that is rain, sleet, or snow. And then it is going to collect into rivers, lakes, streams, oceans as runoff. And then we're going to begin the cycle again. Okay, so we're not making any more water, but our water is in a part of a cycle, up and down, up and down. As we said when we were talking about the biome earlier, water makes up 70% of the earth, and 30% of the earth is land. Okay, so of our water supply, most of it is salt water. 97% is in the oceans and the seas, and it is salty. You can't drink it. And so the process of taking that salt out of the salt water to make it potable is called desalination. okay? And you have plants that do this, and especially in areas that don't have much water, it is actually life-saving to be able to take that salt out of the water, out of the seawater, to make it drinkable. 3% of the waters in the water supply of the earth is fresh water. Rivers, lakes, ponds, underground, these are our wells, streams. But look at how much of that is actually free. Only 1/3 of that 3% is free. 2/3 of it is frozen. And this would be your glaciers, your ice up at the poles. Seasons affect us a lot, and and we know about the seasons. We do have seasons in the South. Some people may feel like we only have two, but we do. We have all 4 seasons, however brief spring may be. But they do impact us a lot. It affects the conditions in the atmosphere and on the earth that create our weather. Okay, so as the earth revolves around the sun, it's tilted. The earth is tilted at 23.5-degree angle in relation to the sun. And so that means that different parts of the earth receive the direct rays of the sun for more hours of the day at certain times of the year, and that causes seasons. You have your equinox and your solstice. These are the shortest and the longest days of the year. That would be the solstice. And the equinox is kind of in the middle. These, the days and the nights all over the world are equal in length. And this is the beginning of spring and autumn. And we see this in March and September. And then the solstice is in the northern hemisphere. The summer solstice is the beginning of summer and is the longest day. And in the winter, the solstice is the shortest day of the year. And it's the opposite in the southern hemisphere. Okay. Wish I had a diagram for that. I might need to find one. Again, we talked about this. Oh, I'm going to go back. A few things about this. I'll try to find a good diagram, but you can see if you look when we're talking about latitudes, you can see the tilt of the earth and the diagram there. But whatever is the closest to the sun is the area that's going to get the most sun. So you would see the poles getting either no. Okay, I'm going to try to say this again. The poles would either get very little sunlight or very little nighttime, very little dusk. So the earth, its seasons, is because of the tilt of the earth and the way that we go around. So I think I muddled that up. If you have any questions on that, ask me. But make sure that you fill in your notes guide. When you're done, take a picture and submit it. This is the day 3, the earth. Again, I put both of these together just because of it would normally take us 2 days to do this in class. So get that done and turned in. Thanks.